The last one, which I will be pretty briefly discussing, is the one where we discussed the multi-objective optimization. So we said that in many problems, what happens is that there are multiple objective functions. So there are multiple objective functions, and my problem really in such situations is when there are multiple objective functions that my evolution happens by one objective function, and therefore I made a joke what many people do. They say that I have got two objective functions, I need one, so it's the first objective function plus w2 times the second objective functions, and that's bad because how do I get w? How do I get w? I don't know. That's bad. And I made a fun of it. Don't do that. Don't convert multiple objective function into one objective function by taking a weighted addition. And guess what? Even after speaking so much, what did I do? I said my loss function is mean square error plus lambda times regularization. First objective function, second objective function. So what I told you not to do, I've done exactly the same thing. And because of that, it is potentially a bad idea. It's potentially a bad idea. Now you already know the basics of it, so there's no point in repeating it. You know how to do evolution with a variable architecture neural network. You know how to take distance values for diversity preservation. You know how to calculate the mean square error. You know how to calculate the regularization function. And therefore, let's just take the... So there'll be some decision space here which is not important. However, a point in decision space will be mapped into what is the objective space. Which will have one loss function as the mean square error and the other objective function as the regularization or the complexity. Now, I said that these two need to have a trade-off for best results. Otherwise, optimizing one objective automatically optimizes the other. And let's establish if this is a valid problem or if mean square error and complexity or regularization are having a natural trade-off between each other. And if that will be the case, then that will be an interesting thing to do, and I will be taking it up. And otherwise, if there is no such trade-off, then optimizing one will automatically optimize the other. So what I do is I take a neural network which has an extremely small complexity, one hidden neural network, small complexity. And of course, you know what will happen is if this is my input to output and this is the natural training data, so you can guess the shape. I took just one neuron, so the complexity was minimum, and because I just took one neuron, the complexity was minimum, it can potentially just regress it as a straight line, which means the mean square error will be extremely high. So when the complexity is small, the mean square error is extremely high. When the complexity is high, and of course this is what is called as the underfit, When the complexity is high, so I'll get in a network which regresses like this. I should have done it a slightly better. So the mean square error is actually 0 because I've got extremely large complexity. So when the complexity is high, I can actually learn this complex function as well. So mean square error is actually 0, but I will not write down 0, I'll write down small, and this one is overfit. And if this one is moderate, this one is moderate, this is the ideal fit. And this is how the ideal fit will look like. Oops. So let's mention it over here. So this is underfit, which is characterized by high training error and high testing error, and it's of course bad. This one is called as the overfit. Happens when the complexity is very high. You get very small training error. And you get high testing error. And this one is, of course, what is an ideal fit. So that's moderate training error and also a moderate testing error. That's what I want to get. So let's look at the trade-off which exists over here in this curve. So when the mean square error is high, which is bad, the complexity is small, which is good, and when the mean square error is small, which is good, the complexity is high, which is bad. So mean square error is the opposite of complexity. That means you work very hard to optimize one, the other goes equally bad. You work very hard to optimize the second, the first one goes very bad. You can only optimize one, the other will become bad. So that's unlike optimizing one also optimizes the other, in which you have a choice. Just optimize one of them and the problems are easier. So we've got the same problem. And finally, I'm not showing the evolution in the decision space. Let's just show it in the objective space. So I have the mean square error and the complexity. And I'll get a Pareto front over here. So diverse and non-dominated. Now the problem is that I finally need just one neural network. I don't need so many neural networks. Which one do I select? You can do a knee analysis, which is the one which has the best trade-off. So it neither has a very high MSE, it's equally low, nor it has a very high complexity, it's equally low. But then there's something interesting that you can do over here. So let's say this is the ANN A, B, C, D, E, F, G, H. Now what I do is I make a ANN like this: A, B, C, D, E, F, G, and H. So I apply my input on all the neural networks and I take the output from all the neural network and I just do a averaging. And that's my output. This one is also called as an ensemble. So an ensemble is that sometimes one person doesn't solve the assignment correctly. So you ask 10 people to solve it up, and then you combine the solutions of all the 10 students. That's an ensemble. So here I did not have one good neural network. I had 7 of them. I had 8 of them. So I say that instead of making one neural network solve the entire problem, I give it to all 7 of them. I average out the solution. I fuse the solution. So there's a problem, all 7 of them solve the problem, and then I just take the average of them. Now, ideally, what happens is that you would expect that the performance of an ensemble is the average of the average performance of all of them. So it doesn't perform worse than the worst, it doesn't perform better than the better, and it mostly gives an average performance. That's what averaging mostly does. Now, by experiments, what turns out, it's actually true that an ensemble always gives in more or less the average performance, like every other neural network. You're just taking the average of the output, the performance also gets averaged, with one exception. So, and the exception is an ensemble performs very well if all members of the ensemble are good by some virtues. So here all of them were good because mostly they had small mean square error, but the ones that also had a large mean square error, they had a small complexity. So in some virtue they were good. All members are diverse. It's actually a contradictory statement, because if you call an expert of a problem, all experts usually will tell you the same thing. If I ask 1 plus 1, what is it? I call number of experts, they all of them tell me it's 2. But how you normally make committees when it comes to project presentations and all, we have a fundamental that we call experts who are diverse. So somebody who is very lenient, somebody who is very strict, somebody who is very harsh on the report, somebody who takes very long vivas, somebody who is very good in vision, somebody who is very good in learning. So we call in people who are diverse, sometimes from different institutions, and they look at different perspectives and they give different opinions. They focus upon different things. And that's why it makes an overall a great committee. That's something that's being used in every committee for evaluation of every kind. Call in diverse experts from diverse geographical area, from diverse background, from diverse experience. And they're all experts, so they should say the same thing, but they'll focus upon different areas and the views may not completely match. And then when we average them out, we get an overall idea. Somebody has an idea which is narrowed down someplace, some other which is narrowed down on some place. When we take an average of them, we get overall a broader perspective. And that's exactly what algorithms like adaptive boosting does. So you make in one neural network which is good, but then you create another one as a part of the ensemble which is better on things which this network wasn't good at. You create a third one which is better on the data where the first two were not good at. And here exactly the same thing is happening. So my network is not only individually good, it's also diverse, because objective space diversity was one of my criterions. Objective space diversity was one of my criterions. So some are good in MSE, some are good in complexities, they are diverse. And adaptive boosting theory, when all your members are diverse and individually good, it makes an ensemble which is better than the best of the networks. And that's exactly the same theory which is going out over here. So I created an ensemble of networks which are individually good and diverse, and that's why I don't need to select one neural network. I use all the neural networks to solve the problem and just take the average, or the fusion. It's more generally called as the fusion of all of them. And because I've taken the fusion of all of them, the algorithm, it actually turns out to be interesting, to be get better. And because it turns out to be interesting and it turns out to be better, that's why I don't select one neural network. So overall, it was a problem where diversity, it was a problem where we had two objectives, and for the first time we solved it the way we should be solving it up, in a multi-objective optimization manner. And we also addressed the last problem, that how do I select one neural network, one individual, using multi-criterion decision making? No, I don't need to select it up. I have an ensemble of diverse individuals who are individually competitive, and therefore it makes an absolutely great ensemble whose performance potentially overbeats the performance of the best network. And with this, that will be all for today.